Imagine walking into a pristine, state-of-the-art sports arena, or, even just a newly renovated local community gym.
Yeah, a really nice one.
Right? A nice one. You walk through the front doors, and the aesthetic is just flawless. The hardwood floor is gleaming under these perfectly balanced, glare-free LED lights. The ambient air is cool, it's crisp, and it smells faintly of, like, clean citrus rather than lingering sweat.
Which is always a relief.
Exactly. The bleachers are spotless, the scoreboards are humming quietly, and the whole environment just feels effortless. But the reality is, behind the scenes of that flawless aesthetic is a relentless, highly calculated, continuous operation.
Oh, absolutely. It's a war zone back there.
It really is. It's an operational war against physical decay, and the battleground is literally everywhere you look. Today, we are taking a formidable stack of materials on facility maintenance and sports management, and we're going to extract the underlying systems that keep these structures standing.
And one metric in these sources clearly illustrates the stakes here. Facility maintenance was historically considered an afterthought in sports management, like a line item you only addressed when something definitively broke.
Right, when the roof caves in.
Exactly.
Right.
But today, maintenance costs are surpassed by only one other thing in an organization's operational budget, and that is energy expenses. It is the second most expensive aspect of running a facility.
Wow. Second most expensive.
Yeah, it is a striking financial reality when you examine the balance sheets of these organizations. As civic and private infrastructure ages, facility managers face this exponential curve in maintenance expenses. The era of simply waiting for a component to fail is long gone.
Has to be.
It does. So today, our mission in this deep dive is to deconstruct that evolution of facility maintenance. We'll explore the critical, financially driven shift from reactive strategies to proactive management.
You are going to analyze the underlying physics and chemistry of the grueling interior and exterior checklists that preserve these building envelopes.
Yes, and we will unpack the structural mechanics of the capital improvement planning process, the CIP. That dictates how millions of dollars in municipal or private funds are allocated over decades.
And finally, we will examine the technical science of the ground beneath the athlete's feet, contrasting the biomechanics of specialized sports flooring with the really complex environmental management of synthetic turf.
By the time we conclude, you will never look at a sports facility, or any commercial building for that matter, the exact same way.
Okay, let's unpack this. The sources present a sharp dichotomy between two distinct management philosophies. There is the legacy approach, which the literature refers to as the squeaky wheel method.
Ah, the squeaky wheel.
Right, it's a purely reactive posture. A facility supervisor essentially defers all action until a structural or mechanical failure forces their hand. They wait for the wheel to squeak. Or, more accurately in this context, they wait for the boiler to fail, the roof to leak, or the lighting grid to short circuit.
And from an actuarial and management perspective, that is a financially ruinous strategy. Completely. The psychology behind this squeaky wheel approach is rooted in the illusion of short-term savings.
Because you're not spending money today.
Right. If you aren't deploying labor or purchasing parts today, the quarterly operating budget looks healthier. But when that inevitable failure occurs, the nature of the problem shifts from a routine maintenance task to a full-blown operational crisis.
Yeah.
The mathematics of a reactive method guarantee exponentially higher costs. You're suddenly paying premium expedited rates for emergency contractors. You are incurring expedited shipping costs for heavy replacement parts.
And you have to factor in the downtime.
Exactly. You face severe operational downtime, which translates directly to lost revenue, whether that is canceled league games, refunded ticket sales, or frozen membership dues. And most critically, you introduce severe liability risks regarding the safety of the patrons and the athletes.
So contrast that approach with what the industry defines as routine maintenance.
Right.
Routine maintenance, as defined here, seems highly specific in its parameters. It encompasses tasks that do not pose an immediate threat to life or property, they don't cause major operational disruptions, and they do not require panic-driven corrective action.
Yes.
It's the invisible, scheduled intervention. But the primary objective isn't cosmetic. It is fundamentally about offsetting the depreciation of the asset.
Precisely. Through rigorous routine maintenance, you are systematically enhancing the serviceable lifespan of the building. You are buying years, sometimes decades, of viability for your infrastructure by managing the rate of decay rather than reacting to its climax.
That makes sense.
A proactive manager views routine maintenance not as an expense, but as an annuity. An annuity that pays dividends by delaying the massive capital costs of a full replacement.
The sources emphasize, however, that this proactive framework cannot exist in a vacuum. It requires a highly structured communication protocol.
It does.
The text details a specific five-step communication process: clarifying the problem, getting participation, transmitting decisions, motivating others, and measuring effectiveness. Now, while this resembles standard corporate management theory, I imagine the application in sports facility management carries significantly higher stakes, especially during a live event.
If we connect this to the bigger picture, you're correct that these are fundamental leadership principles, but the specific environment of a sports facility elevates their importance. Let's ground this in a high-stakes scenario.
Okay, let's hear it.
Imagine it is 4 hours before a heavily broadcasted major basketball tournament, and the primary HVAC chiller for the arena fails.
Oh, that's a nightmare.
Absolute nightmare. The ambient temperature is rising by the minute. Under step 1, clarifying the problem, the facility manager cannot afford to panic and simply declare a general emergency. They must isolate the technical reality.
Yeah, they need specifics.
Did a compressor blow? Is there a refrigerant leak? Is it a localized software fault in a building automation system? You have to clarify the precise nature of the failure before escalating the issue.
Because if you transmit a vague or incorrect assessment, you initiate the wrong cascade of solutions.
Exactly. Which leads directly to step 2, getting participation. In a crisis, a manager shouldn't just issue unilateral directives. You pull in your lead mechanical engineer, your tournament director, and perhaps the broadcast liaison. You ask targeted questions.
Like, can we bypass the faulty chiller?
Yes. Can we divert chilled water from the practice facility? How much time do we have before the court surface begins to sweat due to humidity? Engaging those stakeholders fosters rapid technical innovation.
And then you arrive at step 3, transmitting ideas and decisions.
Right. This requires surgical precision in your language. You inform the mechanical team exactly which vans to isolate, and you inform the tournament director exactly what temperature parameters they can expect by tip-off. Ambiguity in this phase leads to operational paralysis.
And step 4, motivating others. That shifts the focus from data transfer to execution, right?
It does. You are securing the commitment of a stressed maintenance crew to perform a complex high-pressure bypass safely and efficiently.
And step 5 is the phase that seems most frequently neglected in general operations, measuring the effectiveness.
So, without a doubt.
It is the continuous feedback loop. If the directive was to divert chilled water from the practice facility, you have to verify if the ambient temperature in the main arena actually stabilized. If the humidity is still rising and the maple floor is becoming slick, the solution failed, and you must instantly cycle back to step 1.
That continuous feedback loop is the true differentiator. It's the intangible communication system that ultimately sustains the tangible physical systems.
Right.
Without it, even a facility with a pristine maintenance schedule will collapse under the pressure of an unexpected anomaly.
Let's transition from the intangible systems to the physical reality of the building envelope. The exterior inspection checklist detailed in the sources is exhaustive.
It is massive.
It reads like a masterclass in building pathology. Starting at the highest elevation, the protocol for roofs dictates formal inspections at least twice a year, specifically in the spring and fall, as well as immediately following severe weather events.
The temporal spacing of those inspections is highly strategic.
How so?
Well, the spring inspection is designed to assess and remediate the damage inflicted by the winter cycle. The freezing, the thawing, and the sheer weight of ice accumulation that tests the elasticity of the roof membrane.
And the fall?
The fall inspection serves to clear the accumulation of summer debris, like leaves and organic matter, and to verify the integrity of all seals before the winter cycle begins again.
One detail that underscores the complexity here is the requirement for a comprehensive moisture survey every 5 years to detect wet insulation.
Yes.
Most people think of a roof leak as water dripping directly onto the gymnasium floor. But a compromised membrane often just allows water to seep into the insulation layer underneath where it sits hidden.
And that hidden saturation is arguably more destructive than a visible leak.
Really more destructive.
Absolutely. When roof insulation becomes saturated with water, it loses its thermal resistance, which is commonly referred to as its R value. Water is an excellent conductor of heat.
Oh, right.
Once that insulation is wet, the facility's HVAC system is suddenly forced to work significantly harder to heat or cool a building that has lost its thermal envelope. A facility manager might notice a 30% spike in their monthly energy expenditure before they ever see a single drop of water inside the building.
So how do they even find it if they can't see it leaking?
They employ infrared thermography during these surveys. By scanning the roof at dusk as the dry areas cool down rapidly, the waterlogged insulation retains the heat of the day. It glows vividly on the infrared camera, allowing technicians to pinpoint and replace the compromised sections before the underlying steel roof deck begins to rust.
That is fascinating. The documentation also offers a stark warning about warranties, specifically noting that commercial roof warranties typically do not cover damage resulting from clogged drains. I found the counterintuitive nature of this particularly striking.
It catches a lot of people off guard.
A manager might assume a primary structural failure is always covered. But if the root cause is deferred maintenance on a simple drain grate, the liability shifts entirely.
You have to remember that water possesses immense density and weight.
Right.
When a primary drain clogs with organic debris, the roof essentially transforms into a shallow swimming pool. A standard commercial roof is not engineered to bear the hydrostatic load of pooled water. As the water deepens, the structural load capacity of the steel joists is exceeded, leading to severe deflection or even total collapse.
And because the failure originated from a lack of routine maintenance, clearing the debris, the manufacturer's warranty is entirely voided.
Completely voided. This is why the protocol also mandates walking the perimeter to inspect sheet metal copings, examining the roof-to-wall connections, and scrutinizing the flashings at the equipment curbs for any tearing or separation caused by the building settling.
There's also a highly specific directive to check for corrosion on metal roofs caused by the condensate dripping from the copper coils of rooftop HVAC units. It isn't just atmospheric moisture causing the rust, it's a chemical reaction initiated by the air conditioning equipment itself. How does the HVAC chemistry actually attack the roof?
You are looking at the principles of galvanic corrosion.
Galvanic corrosion.
Yes. When condensation forms on the copper coils of an air conditioning unit and drips onto the roof, that water carries dissolved trace amounts of copper ions.
Okay.
When those copper ions make contact with a galvanized steel or aluminum roof surface, a localized electrochemical reaction occurs. Because copper is a more noble metal on the galvanic scale than zinc or aluminum, it accelerates the oxidation, the rusting of the roof metal at an alarming rate.
So the AC is basically eating the roof.
Essentially, yes. It is a highly specific, rapid deterioration that a purely reactive manager would never anticipate until the roof membrane is entirely perforated. Furthermore, this is why the checklist stringently limits foot traffic on the roof, requiring designated walkway pads. Every footstep on a standard single-ply roof membrane degrades its protective UV coating and introduces microabrasions.
Moving down from the roof, we reach the exterior walls, and the terminology used to describe their degradation is profound. The checklist categorizes vulnerabilities by material.
Yes, it gets very specific.
For masonry and mortar, the focus is on locating loose or missing joints. For brickwork, the inspector is hunting for localized stains, wet spots, and a phenomenon known as spalling.
Right, spalling is basically this destructive physical process driven by temperature fluctuations. You see, brick and mortar are inherently porous materials.
Right, they absorb water.
Exactly. So if the exterior sealant fails, water infiltrates that substrate. And when the ambient temperature drops below freezing, that trapped water crystallizes into ice.
Which expands.
By about 9% in volume, yeah. And that internal expansion generates an incredible outward pressure, often exceeding the tensile strength of the fired clay, which physically blows the outer face of the brick off.
It just pops the face right off the brick.
It presents visually as the brick, flaking or peeling away, leaving a rough, highly vulnerable interior exposed to further weathering.
Closely related to spalling on the checklist is efflorescence. It presents as those chalky, white, crystalline deposits you frequently see on the exterior of brick buildings. It often looks like a harmless cosmetic issue, perhaps just dried hard water, but the sources frame it as a critical diagnostic indicator.
Efflorescence is a visible symptom of a hidden moisture transport mechanism. It occurs when water infiltrates the masonry assembly and dissolves the natural, water-soluble salts present within the mortar, concrete, or the brick itself.
Okay, so the water dissolves the salt. Then what?
Through capillary action, the water migrates toward the exterior surface of the wall. When water evaporates into the air, it leaves those dissolved salt crystals behind on the surface. While the salt itself doesn't destroy the brick, it provides definitive proof that moisture is actively traveling through the wall assembly, indicating a failure in the building's waterproofing membrane or flashing.
When the checklist shifts to stucco and plaster, it mandates inspections for localized cracking, soft spots, and bulging. And for siding and wooden sheathing, inspectors are directed to scrutinize the boards for rot, splitting, and what the text ominously refers to as signs of veins of dirt.
Veins of dirt.
Yeah,
What exactly are those?
those visual veins are not merely accumulated grime, they are the architectural constructs of subterranean termites.
Termites.
Yes. Termites require a highly humid microenvironment to survive. Exposure to dry air and sunlight is lethal to them. To safely traverse from their colonies in the soil up into the cellulosic, wooden structures of a facility, they construct these protective mud tubes or veins along the exterior foundation. So they build their own little climate-controlled tunnels.
Exactly. Identifying these tubes means you are not dealing with a simple cleaning task. You are observing an active biological threat systematically consuming the structural integrity of your facility.
Wow. The perimeter inspection then moves to exterior finishes and what is termed facility fenestration. Regarding painted surfaces, the protocol looks for blistering, peeling, and a specific pattern called alligatoring, where the paint film clacks into rigid scales resembling reptile skin.
Alligatoring is an engineering failure of the coating system. It typically manifests when a hard, rigid top coat of paint is improperly applied over a softer, more flexible underlying primer, or when the top coat is applied before the bottom coat has fully cured.
So they expand at different rates.
Exactly. As the building's substrate expands and contracts with daily thermal cycling, the underlying layer flexes, but the rigid top coat cannot. It shears and cracks into that distinct scaly pattern. Once alligatoring occurs, the protective barrier is broken, allowing moisture direct access to the substrate.
The text also highlights the necessity of inspecting decorative structural elements, such as stone anchors and steel brackets, for rust-induced expansion.
Yes, much like the freezing water in spalling brick, when iron oxidizes into rust, it expands to several times its original volume. If a steel anchor is embedded inside a stone facade and begins to rust, that expansion creates internal pressure that can fracture the stone wide open, creating a severe falling hazard.
The term fenestration was one I had to clarify. It refers to the design, placement, and maintenance of all deliberate openings within the building envelope. The doors, windows, skylights, and louvers.
Fenestration represents the deliberate vulnerabilities in your building's armor. These penetrations are critical because they govern natural daylighting, ventilation, emergency egress, and overall thermal efficiency.
The inspection requires meticulous assessment of door alignment, the functionality of panic hardware, and the integrity of weather stripping.
For windows, inspectors must verify the smooth operation of the sashes, the state of the glazing putty, which secures the glass panes and repels water, and the condition of the perimeter caulking. A misaligned heavy glass entry door isn't just an annoyance for patrons. It represents a vulnerability in the security perimeter and a continuous leak in the conditioned air envelope that will measurably inflate the annual energy budget.
Finally, the exterior checklist concludes with the decks and grounds. The directive for wooden porches or structural supports is to physically probe the material with a screwdriver to locate internal soft spots, indicating hidden wood rot.
Have to get in there and test it.
Furthermore, managers must survey the asphalt driveways and concrete sidewalks for heaves or depressions that constitute trip hazards. They must inspect storm drains for obstruction, and perhaps most importantly, evaluate retaining walls for cracking, spalling, or any signs of leaning and bulging.
The structural failure of a retaining wall is a perfect illustration of the primary antagonist in facility management. A retaining wall leans or bulges when the lateral earth pressure behind it exceeds its design capacity. And what causes that pressure to spike suddenly? Soil saturation.
Water again.
Always water. When poor drainage allows water to saturate the soil behind the wall, you are introducing massive hydrostatic pressure. Water is heavy. The soil acts like a sponge, expanding and pushing relentlessly against the concrete.
Right.
If we synthesize this entire exterior checklist, from the roof thermography to the galvanic corrosion, the spalling brick, the alligatoring paint, and the bulging retaining walls, the common denominator is unmistakable. Water is the universal solvent and the ultimate enemy of infrastructure.
The entire exterior maintenance protocol is fundamentally a complex moisture mitigation strategy.
If a facility manager can successfully dictate where the water flows, the building survives.
That principle of moisture mitigation provides a perfect conceptual bridge as we transition inside the facility. Here's where it gets really interesting. When the exterior defenses we just discussed fail, the consequences inevitably manifest internally. The interior inspection checklist is just as relentless.
It really is.
Starting in the lowest levels, the basements and mechanical rooms, The protocol requires inspecting the foundation walls for visible cracks, water stains, and structural issues like bulging. If a basement wall is bowing inward, you are witnessing the direct result of that same hydrostatic pressure we discussed with the retaining walls. The soil outside is saturated, and the water is seeking the path of least resistance into the building.
Exactly. The exterior failure becomes an interior crisis. Moving from the foundation to the mechanical systems, the HVAC system serves as the respiratory and circulatory system of the facility. The inspection here transcends simply verifying the thermostat setting.
What else are they looking for?
Technicians must conduct continuous air quality testing, verify the balance of air circulation to prevent stagnant zones, and meticulously inspect filtration systems for mold spores, which thrive in the dark, damp environments created by condensation.
The depth of the HVAC electrical inspection is particularly intense. The maintenance teams are required to verify that all electrical connections are snug and secure. They are taking precise voltage and amperage readings across the circuits.
The physics behind that requirement are non-negotiable. Over time, the micro-vibrations of a massive commercial air handler can slowly loosen the physical electrical connections at the terminal blocks.
Just from the machine vibrating day after day.
Yes, a loose connection reduces the contact area for the electrical current, which significantly increases electrical resistance. According to Ohm's law, increased resistance in a high current circuit generates immense localized heat.
Oh, wow.
If left unchecked, that loose connection will eventually melt the surrounding wire insulation and trigger an electrical fire.
That is terrifying.
Additionally, the checklist mandates verifying the clearance of the condensate drain lines. Just like the primary roof drains, the cooling coils in an HVAC system extract gallons of water from the humid air daily. If that drain line clogs with algae or dust, the drain pan overflows, sending water cascading down through the ceilings and drywall of the facility, destroying the interior finishes.
Water strikes again.
Furthermore, all gas and oil supply lines fueling the boilers must be inspected for the slightest blemishes or leaks, as a failure there introduces catastrophic explosive potential.
Shifting from the mechanical rooms to the areas where patrons actively engage, the protocol regarding sports and fitness equipment is incredibly nuanced. If you frequent a gym, you interact with this hardware daily. The sources dictate a rigorous daily cleaning routine aimed at removing dust, dirt, and human sweat. Sweat is highly saline and remarkably corrosive to moving parts.
It destroys metal.
But one specific directive stands out. For treadmills, the protocol explicitly requires technicians to remove the front cover and vacuum underneath it to prevent dust accumulation on the motor.
The internal compartment of a commercial treadmill is a volatile microenvironment. You have a high-torque electric drive motor and a heavy rubber belt scribbing continuously across a frictionless deck. This friction generates a substantial static electrical charge, transforming the entire machine into a powerful dust magnet.
I didn't even think of the static electricity aspect.
In a commercial fitness environment, that ambient dust is a dense compound of aerosolized skin cells, cotton clothing fibers, dirt tracked in from athletic shoes, and dried salts from sweat. If the maintenance staff fails to remove that motor cover and extract the debris, this dense, insulating blanket of dust coats the copper windings of the motor and the delicate components of a lower control board.
It just bakes it.
It traps the ambient heat generated by the motor. The system runs increasingly hotter until the thermal overload protections fail and the motor burns out entirely. A simple 5-minute vacuuming protocol literally preserves the lifespan of a multi-thousand-dollar drive motor.
The maintenance protocol is equally strict regarding the chemistry of the cleaning agents used on this equipment. The text explicitly prohibits the use of harsh chemicals, specifically warning against ammonia, bleach, or acid-based cleaning fluids on exercise machines, noting they induce malfunction and permanent damage.
Bleach and ammonia are highly reactive, oxidizing agents. While they are exceptional disinfectants for non-porous ceramic surfaces in a restroom, they are highly destructive to the engineered polymers and metals of fitness equipment.
What did they actually do to the machines?
Well, ammonia will rapidly degrade the specialized thermoplastic elastomers used on the hand grips, causing them to become sticky and eventually disintegrate. Bleach will strip the protective clear coat anodization off the aluminum and steel frames, exposing the raw metal to the corrosive salts in the patron's sweat, leading to rapid deep rust.
Which you don't want on a weight machine.
Not at all. And most critically, these chemicals will craze and cloud the polycarbonate screens, overlaying the digital interfaces, rendering the touch screens unresponsive. Facility managers are bound to utilize only pH-neutral, quaternary ammonium compounds specified by the equipment manufacturers to maintain the integrity of the hardware.
The documentation also touches on the repairs of these machines, establishing an absolute rule. Broken or worn components must only be replaced with genuine, manufacturer-approved parts. A facility manager might look at a frayed steel cable on a lat pull-down machine and realize they can purchase a generic steel cable of identical thickness at a local hardware store for a fraction of the cost, minimizing downtime. From a purely operational standpoint, if the generic cable possesses the exact same tensile strength as the branded one, why couldn't a manager utilize it to save time and budget?
That is an excellent question that highlights the intersection of operational efficiency and legal liability. It is entirely possible that the generic cable possesses the requisite tensile strength. However, the moment a facility manager installs a non-original equipment manufacturer or OEM part, they unilaterally void the indemnification provided by the equipment manufacturer.
So the manufacturer is off the hook.
Completely. Let us assume that the generic cable is installed and a month later, a patron is lifting 300 pounds. The cable switch fails, the weight stack drops, and the patron suffers a severe spinal injury. During the ensuing litigation, the forensic investigation will identify the generic part. Because the facility altered the engineered design of the machine with an unapproved component, the manufacturer is completely shielded from liability.
And the facility takes all the blame.
The facility organization, and potentially the manager personally, assumes 100% of the legal and financial liability for the injury due to a breach of their duty of care. Adhering exclusively to OEM parts and maintaining meticulous service logs is fundamentally a risk management strategy, not just a mechanical one.
Moving into the locker rooms and restrooms, the maintenance standards escalate further. For locker rooms, the primary directive is absolute. There must be no standing water under any circumstances, particularly in the shower and sauna areas.
Standing water is a massive hazard.
Technicians must continuously monitor and calibrate the mixing valves to ensure shower water temperatures are regulated to prevent scalding injuries. They must verify that dry saunas remain genuinely dry to prevent the accelerated rot of the cedar paneling, and they must constantly test the chemical balance and temperature parameters of hot tubs to prevent bacterial outbreaks like Legionnaire's disease.
Notice how the checklist in these specific zones seamlessly integrates physical maintenance with behavioral security protocols. While inspecting the plumbing, the staff is simultaneously tasked with ensuring there is no suspicious activity or inappropriate behavior.
Right, checking for phones and things.
They must rigidly enforce policies prohibiting the use of cellular phones or electronic recording devices in restricted areas to protect patron privacy. Furthermore, they are trained to identify and address unattended bags, which represents a critical security protocol designed to mitigate theft and address severe safety vulnerabilities. In these high vulnerability zones, facility maintenance is inextricably linked to patron surveillance and psychological comfort.
The meticulous nature of the restroom protocols reinforces that comfort. Staff aren't just instructed to mop the floors, they're directed to systematically disinfect high-contact vectors. The door handles, the lighting switches, the flush actuators, and the faucet sensors.
Everything you touch.
They are responsible for replacing urinal screens and enzymatic blocks, restocking and sanitizing feminine hygiene dispensers, and calibrating the ambient odor control systems. They must even routinely flush the floor drains to ensure the P-traps remain filled with water, preventing toxic sewer gases from venting back into the room. When a patron enters a locker room and feels a sense of security, observes pristine cleanliness, and experiences a perfectly calibrated shower, they are experiencing the culmination of this relentless, microscopic operational checklist.
However, executing that level of microscopic daily detail requires a substantial and consistent operational budget. This raises an important question.
Which is?
We have spent considerable time dissecting routine maintenance, the ongoing daily skirmishes required for the building to survive. But what occurs when patching the membrane of a 30-year-old roof is no longer viable? What is the protocol when an organization needs to replace a $3 million HVAC chiller plant, construct an entirely new aquatic wing, or perform a total structural remediation of a concrete foundation?
That is the threshold where a facility transitions from operating expenses into the realm of capital improvement planning, or the CIP. The sources provide a highly rigid definition of what legally and financially qualifies as a capital improvement project. It is classified as a major, non-recurring expenditure.
And the qualifying criteria are very strict.
Yes, It encompasses the acquisition of new land. It covers new structural construction or significant additions to an existing footprint. It includes major rehabilitation or repair projects, such as a complete roof tear-off or the replacement of a primary HVAC unit, provided the total cost exceeds a threshold of $25,000 and the resulting improvement guarantees a useful life of 10 years or more.
It also applies to the procurement of major equipment, like replacing an entire fleet of motorized bleachers, if the cost exceeds $25,000 and the equipment has a useful life of 5 years or more. Interestingly, it even covers the initial architectural, engineering, and feasibility studies required to conceptualize these massive projects.
The specific parameters of the $25,000 threshold and the 10 or 5-year useful life requirements are critical accounting distinctions. They separate the capital expenditure, CapEx, from the operating expenditure, OpEx. Purchasing 50 cases of HVAC air filters is an operating expense. The filters are consumed rapidly, and the cost is relatively low, so it hits the current year's budget directly.
Conversely, purchasing a $150,000 backup generator that will provide power for 20 years is a capital asset. It is placed on the balance sheet, and its cost is depreciated over its useful life. But a critical insight provided by the text is the planning ecosystem that surrounds the CIP. A capital improvement plan is not drafted in isolation. It is the final derivative of a nested series of strategic, community-driven documents.
The progression through that planning ecosystem demonstrates how deliberate this financial architecture must be. It originates at the highest strategic altitude with the comprehensive plan. This document encapsulates the overarching long-term vision of the organization or municipality. It analyzes macroeconomic trends, demographic shifts, and future community needs.
For example, a city might project a massive population surge in a specific district over the next 20 years, necessitating a new multi-sport complex.
From that broad vision, the process steps down to the strategic plan. This document translates the broad visions of the comprehensive plan into actionable, specific goals. If the comprehensive plan demands better community health, the strategic plan might mandate the expansion of aquatic therapy access or the upgrading of all existing facility lighting to high-efficiency LED systems to reduce the carbon footprint.
Yet, before you can draft the actual CIP to fund those goals, you must conduct a rigorous reality check, which consists of the capital needs study and the subsequent affordability analysis.
The needs study is an exhaustive physical audit. You deploy structural engineers and facility managers to assess the existing infrastructure against the goals of the strategic plan. They might conclude, to meet the goal of expanding our basketball leagues, we must address the main arena. However, the 30-year-old maple floor has been sanded down to the tongue and groove joints. It cannot be refinished again and requires total replacement.
Once the physical need is verified, the affordability analysis applies the financial friction. It asks the difficult questions. Can the municipality actually finance a $500,000 floor replacement? Do we have the tax base to support a new municipal bond measure? Are there state-level grants available for infrastructure upgrades? Or will the debt service on this project cripple our operational budget for the next decade?
Only after surviving that financial scrutiny does the project enter the actual capital improvement plan. The CIP serves as the master blueprint that translates the strategic goals and physical needs into a structured, prioritized, and fully funded timeline. It explicitly outlines when the money will be spent and where it originates. The CIP then directly informs the annual operating and capital budgets, ensuring the organization balances the short-term function of buying cleaning supplies with the long-term growth of replacing the roof.
To manage the sheer complexity of that financial choreography, the literature outlines a rigid 5-step CIP process. Step 1 is project submission. This is the intake phase, where various departments, stakeholders, athletic directors, and facility managers formally submit their proposals and justifications for what requires construction or replacement.
Step 2 is evaluation and selection. This is essentially a brutal triage phase. The governing committee must evaluate all submissions against a matrix of urgency and feasibility. Does a proposal address an imminent life safety or ADA compliance issue, or is it merely an aesthetic upgrade? They must separate the critical imperatives from the operational desires.
Step 3 is the financial analysis. Once the critical projects survive triage, the finance department must architect the funding mechanisms, whether that involves issuing general obligation bonds, securing private philanthropy, or reallocating existing tax revenues.
Step 4 involves plan preparation. This is where the logistics become highly specific. If the approved project is a massive multi-million-dollar stadium expansion, the CIP document will phase the construction and the funding disbursement over several fiscal years to prevent bankrupting the organization.
Finally, step 5 is review and adoption. The finalized draft of the CIP is presented to the ultimate governing body, the City Council, the University Board of Regents, or the Corporate Board of Directors, for public review, debate, and formal approval. Once adopted, the CIP becomes the legally binding financial framework for the facility's future.
This systemic overview raises an important operational question. How does a facility manager bridge the gap between a macro-level 10-year capital improvement plan and the micro-level daily requirements of keeping the building functional? The mechanism that bridges that divide is the work order system. The work order acts as the central nervous system of facility maintenance. It is the formal, trackable request communicating the specific need for services, labor, or materials.
The documentation categorizes these work orders into 3 distinct operational tiers to govern prioritization. The highest priority is the emergency work order. These denote situations requiring immediate, drop-everything intervention to mitigate imminent hazards, severe safety risks, or catastrophic operational disruptions. This is the scenario where a pressurized water main ruptures directly above the main electrical switchgear room.
The second tier comprises urgent work orders. These tasks demand rapid attention to restore normal function or prevent further damage, but they do not constitute an immediate threat to life or the primary structure. For instance, an entire bank of halide lights fails over Section 104 of the bleachers. It must be rectified before the broadcast event the following evening, but it doesn't require evacuating the building today.
The third tier is the routine work order. These are the preventative scheduled tasks that maintain the baseline efficiency we discussed earlier. Replacing the HVAC filters quarterly, lubricating the elliptical drivetrains, or performing the spring roof inspection.
The text also notes a significant operational shift. Modern facilities increasingly utilize sophisticated app-based tracking systems to automate the routing of these work orders, monitor technician efficiency, and predict future failures. Furthermore, to control operational bloat, there's a prominent industry trend toward outsourcing the routine custodial and groundskeeping work orders to specialized third-party contractors, trading direct oversight for fixed cost efficiency.
All of these systems, the exterior moisture mitigation, the interior mechanical maintenance, the complex financial engineering of the CIP, and the daily routing of work orders, ultimately serve one primary purpose. They exist to support the specific physical space where the actual athletic endeavor occurs.
Which brings us to the literal foundation of the sports facility, the flooring and turf. The source material provides a deeply technical analysis of the engineering behind wood floors and synthetic turf systems. Let's begin with the traditional indoor surface, the wood floor. It is important to realize this isn't simply a layer of maple planks nailed over a concrete slab.
Far from it.
The text details the anatomy of the anchored subfloor system. In this specific configuration, the top layer of premium maple flooring is attached to a complex subfloor matrix, often involving vapor barriers, resilient shock pads, and plywood sleepers, which is then anchored directly to the concrete foundation using mechanical fasteners or specialized adhesives.
The engineering of the subfloor dictates the performance of the entire system. A structural concrete slab possesses zero elasticity. It is entirely rigid. By anchoring the maple system to the concrete, the floor gains immense dimensional stability. It is perfectly suited for facilities anticipating heavy, multi-use foot traffic, such as trade shows or graduations, because the anchored system is highly resistant to shifting, buckling, or warping under variable loads.
But there is a trade-off.
Yes. The literature highlights a critical biomechanical trade-off. An anchored system lacks the vertical flexibility and superior shock absorption characteristic of floating subfloor systems.
And when analyzing the interaction between the athlete and the surface of that wood, the text introduces a fascinating physics concept called the sliding effect, formerly known as the coefficient of friction. It is the precise measurement of the resistance to motion between the athlete's shoe and the floor finish. It quantifies the balance between grip and slip.
The coefficient of friction is arguably the most critical safety metric in indoor sports flooring. It must be engineered to an exact tolerance. Consider the biomechanics of a basketball player sprinting and abruptly planting their foot to execute a lateral pivot. If the coefficient of friction is too high, meaning the floor is excessively grippy, the floor will not yield when the shoe plants.
The energy has to go somewhere.
Exactly. Because the kinetic energy must go somewhere, the rotational shear force travels straight at the kinetic chain and is absorbed entirely by the athlete's knee or ankle ligaments, frequently resulting in catastrophic ACL or MCL tears.
But if it is too slippery?
If the coefficient is too low, the floor acts like an ice rink, leading to severe loss of traction, uncontrolled slipping, and impact injuries. The specialized polyurethane finishes applied to a maple floor are scientifically formulated and rigorously tested to provide a very specific microslide, allowing the foot to yield just enough to dissipate the rotational force during a pivot while maintaining sufficient grip for rapid forward acceleration.
Preserving that exact coefficient of friction dictates the entirety of the wood floor maintenance life cycle. It is a continuous battle waged daily, weekly, and yearly. On a daily basis, the protocol demands meticulous sweeping and mopping, but the directive is highly specific regarding the method. Technicians must use specialized soft bristle brooms, and when mopping, they must use a lightly damp microfiber mop, absolutely never a soaking wet traditional string mop.
That directive loops back to the fundamental rule we established regarding the building exterior. Water is the ultimate enemy. Maple is a hygroscopic material. It naturally absorbs and releases moisture. If a maintenance worker uses a soaking wet mop, capillary action will draw the excess water down into the microscopic seams between the maple boards.
The wood absorbs it and swells.
Yes, the wood fibers will absorb the water, swell, and expand. Because the boards are packed tightly together, the expansion forces the edges of the boards upward, a permanent deformity known as cupping, which destroys the level playing surface and necessitates incredibly expensive remediation.
Moving to the weekly protocol, the checklist requires deep scrubbing with auto scrubbers and microfiber pads to extract embedded grime and dried sweat. The critical warning here is to ensure the cleaning agents leave zero chemical residue behind. Any lingering sticky residue from an improper cleaner will instantly alter the floor's carefully calibrated coefficient of friction, increasing the grip and elevating the injury risk.
Then the life cycle progresses to the heavy, capital-intensive maintenance phases. First is the midlife rejuvenation, known as recoating, typically performed annually. This is a preventative measure executed before the underlying wood suffers damage. Technicians utilize a process called screening to lightly abrade the uppermost layer of the existing finish, removing minor scuffs and surface imperfections.
They then pour and level a new protective layer of specialized acrylic or polyurethane finish. This phase is also when the facility repaints the court boundary lines and team logos. The paint must be applied and then locked underneath the final clear top coats. Otherwise, the aggressive friction of the athlete's shoes would chip the paint away within a few games. Eventually, however, every 5 to 7 years, the floor requires the ultimate intervention: refinishing.
Refinishing is the nuclear option of wood floor maintenance. It is a massive, highly disruptive undertaking requiring specialized professional contractors. They deploy heavy, ride-on sanding machines and grind the entire surface area of the court all the way down to the bare, raw maple, entirely stripping away the accumulated layers of old finish, paint, and deep gouges.
Wow. All the way to the raw wood.
Once the raw wood is exposed and leveled, they must rebuild the floor's protection from scratch, applying sealers, new paint, and multiple layers of high-build finish. However, a maple floorboard is only 3/4 of an inch thick. There is a structural limit to how much material can be sanded away. A typical sports floor can only survive a finite number of these deep sandings, perhaps 6 or 7 life cycles, before the ton-and groove locking mechanisms become exposed and brittle, at which point the entire floor system is dead and must be completely replaced via a major capital improvement project.
Now, contrast the intricate, moisture-sensitive care required for wood with the management of synthetic turf. Turf is frequently marketed to municipalities and school districts as the ultimate maintenance-free alternative to natural grass. The source material, however, forcefully dismantles that myth. While synthetic turf does eliminate the need for mowing and fertilizer, shifting the financial burden from daily operational costs to massive upfront capital costs, it is decidedly not maintenance-free.
Not even close.
The maintenance checklist for a synthetic field is intensely demanding. Facility teams must regularly decompact and replenish the infill, the thousands of pounds of tiny black rubber crumbs that provide the shock absorption mimicking natural soil. They must apply heavy chemical disinfectants to combat the staph bacteria that thrive in the synthetic fibers. But 2 specific requirements stood out as profoundly counterintuitive: the necessity of complex irrigation systems and the application of specialized chemical sprays. You essentially have to water a plastic field specifically to cool it down, and you have to spray it to neutralize static electricity.
It is a brilliant juxtaposition of material science. When you manage a natural grass field, you irrigate the soil to sustain the biological life of the plant. When you manage a synthetic turf field, you are fighting thermodynamics. The polyethylene plastic fibers and the black crumb rubber infill act as a massive, highly efficient heat sink.
So it absorbs the sun.
On a clear day with an ambient air temperature of 90 degrees Fahrenheit, the surface temperature of a synthetic turf field absorbs the solar radiation and can easily exceed 150 degrees Fahrenheit. At that temperature, the plastic begins to soften, and it becomes a severe burn hazard and heat stroke catalyst for the athletes.
So they have to water it.
Consequently, facility managers are forced to install high-volume water cannons around the perimeter of the field. They must flood the plastic surface shortly before a game, utilizing the rapid evaporation of the water to temporarily draw the heat out of the synthetic material. Furthermore, as players sprint across the field, the friction between their synthetic cleats and the plastic fibers generates immense static electrical charges, which can interfere with wireless broadcast equipment and deliver painful shocks. Therefore, managers must regularly apply anti-static chemical surfactants to the field.
The checklist also places heavy emphasis on a relentless battle against organic matter. The protocol mandates the constant, vigilant removal of any natural debris. If autumn leaves, pine needles, or blown dirt fall onto the turf and are allowed to decompose, they break down into actual soil that becomes permanently trapped deep within the plastic fibers and rubber infill.
That infiltration of organic matter destroys the entire synthetic system. Once real soil is established within the infill matrix, it clogs the engineered drainage perforations in the turf backing, causing the field to flood during rainstorms. Furthermore, airborne weed seeds will inevitably blow onto the field, take root in that decomposed organic matter, and suddenly the facility manager is facing the absurd reality of spraying herbicide to kill real weeds growing out of a $2 million plastic field.
To prevent this, facilities must invest in highly specialized, tractor-pulled sweeping and grooming machines. These devices continuously brush the plastic fibers upright, vacuum up the top layer of infill, mechanically filter out the organic debris, and drop the clean rubber back into the turf. Synthetic turf isn't maintenance-free. It simply requires a completely different, highly mechanized industrial maintenance philosophy.
That perfectly summarizes the transition.
So what does this all mean? We have navigated an incredibly dense journey through the hidden, highly technical reality of these facilities. We began by dismantling the financial illusion of the reactive squeaky wheel approach and examining the critical 5-step communication protocol required to manage a high-stakes mechanical failure. We analyzed the physics of the building envelope, detailing the thermal impacts of wet roof insulation, the galvanic corrosion of metal decks, the expansion forces of spalling brick, and the capillary action of efflorescence.
We covered a lot of ground.
We really did. We moved inside to understand how hydrostatic pressure defeats basements, the microenvironmental dangers of dust inside treadmill motors, and the severe legal liabilities associated with non-OEM replacement parts. We explored the massive financial architecture of the capital improvement planning ecosystem, tracking how a community's vision translates into a multi-million-dollar bond measure. And finally, we broke down the biomechanical mathematics of a maple floor's friction coefficient and the thermodynamic reality of having to irrigate a plastic field.
The overarching synthesis of this material is that a commercial sports facility is not a static architectural object. It is a continuously degrading, dynamic system that demands a highly intelligent, financially backed, proactive methodology to survive its own environment. However, as we conclude, I want to leave you with a final thought regarding the trajectory of this industry. As advanced sensor technology and predictive algorithms become ubiquitous, we are witnessing the dawn of the smart building paradigm.
Smart buildings.
Yes. The facility management of tomorrow will not rely solely on a human physically walking the roof perimeter every spring. We're entering an era where the infrastructure itself is deeply networked. Imagine a near future where the building actively generates its own work orders. Picture a scenario where the roof membrane's embedded moisture sensors instantly ping the facility manager's dashboard the moment thermal resistance drops by 2%, signaling a localized flashing failure weeks before water ever penetrates the insulation. Or consider a maple basketball court laced with piezoelectric sensors that monitor the microslide of the athlete's shoes in real time, instantly notifying the custodial staff the exact moment the coefficient of friction shifts out of the safe biomechanical tolerance zone. The squeaky wheel approach of the past relied on catastrophic physical failure to alert management. The squeaky wheel of the future will be a predictive algorithm diagnosing and communicating the decay long before it ever materializes.
That is a profound and entirely plausible evolution to consider. The transition from a building that simply decays to a building that actively communicates its own pathology. Thank you for joining us on this extensive deep dive into the complex, relentless world of facility maintenance. The next time you walk into a pristine arena or a local gymnasium, take a moment to look up at the air handlers, look down at the maple floor, and appreciate the invisible army, the precise physics, and the rigorous financial planning keeping that structure alive. Keep observing the world around you, keep asking questions, and we will catch you on the next deep dive.